So what we have there is, well, we call it a nuclear magnetic resonance spectrometer, but it's most commonly known as an MRI machine. It's the same technology, doesn't do quite the same thing, but a little bit the same technology. And this is in fact a quantum computer. This is a prototype of a quantum computer. Unfortunately, it will never be a large-scale one because there's some physical limitation. But to this day, this is one of the only prototype that we have to test ideas and to experimentally test ideas of quantum information and implement some small quantum algorithm. Right now, we've been able to, here at IQC with some colleagues from MIT, we've been able to control all the way up to 12 separate quantum bits. So our, the smallest logical unit of quantum information. So it offers us a very good test bed, a very precise test bed for investigating further larger quantum system. So in here we have another prototype of a quantum processor. As I mentioned before with the nuclear magnetic resonance, there was some physical limitation to have a large-scale computer, and one of them is because we're controlling internal state of molecules, it's extremely hard to find good large molecule. This is one reason. And in a system like this, what we're actually doing is we're trying to bring all the expertise developed in the past 50, 60 years in fabrication of semiconductor devices, essentially chips. We are able now to build nanoscale chip, but also to control their quantum states. And to do this, we need a piece of equipment like that, which is called a dilution fridge. And what a dilution fridge does is it cools everything down to 30 millikelvin. So we're almost at the absolute zero. And this is necessary to be able to isolate the quantum effect in semiconductor system. And this particular system here is we use nanowires. So nanowire is, as it says, it's a very tiny wire. And by playing some games with electrical current and voltage, we can trap single electron in small puddles. And each of those electrons can be individually controlled to be our quantum bit and to create quantum algorithms. Of course, easier said than done. Right now we're, the state of the art, we're able to trap 2 or 3 electrons next to each other and control a couple of them. But there's still lots of physics to be figured out, and that's one of the things that we do in a lab like this.